Hey everyone, Mr. Doust here. Hope you're doing well. I realize that some of you have been struggling with these assignments that we're doing. It's a lot harder to do things remotely. So I thought I would make some videos kind of walking you through the solutions, and hopefully that'll help. I won't have my image on every slide. I don't want the file to be too big, but I just want to say hey, and I hope you're doing well. All right, here we are. We're looking at question number 1, which is what is an isotope? And the answer is simply isotopes are versions of the same element with different masses. That means their atomic numbers, the number of protons, are the same. The number of neutrons are different. For question number 2, it says examine the table. Are atoms A and B the same element? Explain how you know. And they're the same element because the number of protons is the same. For question number 3, we're looking at the table at the bottom here. We can see that there are 3 isotopes of hydrogen, hydrogen 1, hydrogen 2, and hydrogen 3. And their masses are 1, 2, and 3 because they have 1 proton and either 0, 1, or 2 neutrons to add up to those numbers. If we look at the sample, it looks like 99% of hydrogen is hydrogen 1, and only a small amount is hydrogen 2 or hydrogen 3. Question number 3 is asking, why do you think the average on the periodic table is 1.01? And this is a bit of a prediction question, so answers will vary, but it's very key. I want you to remember that an individual atom will only have a whole number because it's going to have a whole number of protons and a whole number of neutrons. You can't have part of a proton or part of a neutron. Moving on, question number 4 says, using the above paragraph, which explained how to do the calculation, explain why the mass on the periodic table is a decimal. Well, the answer is it's the calculation of the average of atomic masses. It's a decimal because averages are between the values of the isotopes. In this case, it's a lot closer to 1 because the majority of hydrogen has a mass of 1. But there are some small amounts of hydrogen 2 and hydrogen 3 present, so it's not exactly equal to 1. Looking at question number 5, it says, for hydrogen, which isotope is closest to the mass recorded on the periodic table? Why do you think this is based on the data for hydrogen? Well, we just saw that hydrogen 1 was the most common, but even if we hadn't seen that table, by looking at the average 1.008 on this periodic table, or it's 1.01 on other periodic tables, it's really close to hydrogen 1. There are other isotopes that are there, that they're slightly heavier, so the average is slightly above 1. All right, continuing on with question number 5, I have a screenshot here from a PhET simulation. And in this screenshot, we have a sample of hydrogen as it exists in the universe. And if we look here, almost all of the atoms are hydrogen 1, shown in the purple color. And just a tiny little bit is hydrogen 2, shown in the green color. Because there's so much hydrogen 1, the average is really close to 1, just slightly heavier. With a lot of precision, we can see it's 1.00794 AMU. You might notice that the average number varies a little bit based on the number of decimal places that are provided. Don't worry about that. All of the numbers are pretty consistent with each other. Just some have more decimal places than others. Moving on to question number 6. It says, based on the data in the table, which of these would be the most likely recorded mass of carbon on the periodic table? So in the question, you were given 5 options, but the correct answer was B. The atomic mass of carbon is 12.01. Now, if you didn't have a periodic table, we could still predict that because we see that carbon 12 makes up 99% of the total. So the average is going to be really close to 12. The other elements, carbon 13 and carbon 14, are slightly heavier, so the average is going to be slightly bigger than 12. And here's a screenshot of what carbon looks like in that same PhET simulation. in purple we see is carbon 12, in green is carbon 13. Yeah, the vast majority of carbon is carbon 12, which is why the average is so close to it. You'll notice they left off carbon 14 and some other ones here because they're so small they don't really affect the mass of carbon that much. So for number 7, if you have 1,000 carbon atoms and you pulled out just one, what would its mass most likely be? If I pull out one of these guys, it'd probably be one of the purple ones because those are most common. So I'm probably going to get carbon 12. Okay, question 8 is asking you about sulfur. Sulfur has 3 naturally occurring isotopes, sulfur 32, 33, and 34. And so question 8 just wanted you to fill in the data table. Because it's sulfur, it's number 16. We know protons are going to be 16 for each. In this unit, our atoms are always going to be neutral. So protons will equal electrons. And then if the masses are different, 32, 33, and 34, that must be due to the number of neutrons. Notice that protons plus neutrons equals the mass number. 16 and 16 are 32, 16, 17, 33, 16, 18, and 34. If you're given the mass number, you can just subtract the number of protons to find the number of neutrons. Now, what is the most common isotope of sulfur? I can't just say it's going to be in the middle because most elements aren't evenly distributed. If we look on the periodic table, we can see its average is 32.06. That's really close to 32, suggesting that 32 is the most common. And you can look at the image on the screen. Sulfur 32 is shown in purple. In red is sulfur 34, and sulfur 33, I think the green dots there. So kind of interesting. 32 is most common. It's about 95%. 34 is next most common. It's 4%. And sulfur 33 is the least common of the ones that were in our problem. Moving on to question number 9, looking at this table, this graph. Question was, how many isotopes does hydrogen have? See, there are 3 of them. It's hydrogen, so that each one of those has 1 proton, shown as the lighter gray circle in the center. Why are they different? Number of neutrons. So the neutron count is on the y-axis. Hydrogen 1 has 1 proton and 0 neutrons, adding up to 1. Hydrogen 2 has 1 plus 1, and hydrogen 3 has 1 proton plus 2 neutrons, giving it 3. Question number 10 asked you to fill in the boxes for lithium, beryllium, and boron. I know some people have difficulty getting that to work out. In terms of format, that's okay. As long as you find another way to present the information, you're good. What I want you to notice is that things in the same column, like lithium, have the same number of protons, same atomic number. Lithium has 3 protons. Doesn't matter which isotope we're talking about. But because the neutrons are different, we know the masses are different. The protons plus the neutrons will equal the mass. 3 protons, 3 neutrons gives us lithium 6. 3 protons, 4 neutrons gives us lithium 7. You can see that beryllium has 1 common isotope, beryllium 9. Boron is either boron 10 or boron 11. Again, same protons, but different number of neutrons. All right, I hope this helped, and I will make further videos explaining the other assignments as we go.